Welcome, everybody. Welcome, everybody. Can
Thank
you all
you.
hear me?
Good
Please kindly
morning.
come
Yeah, welcome.
hear me.
Good morning from Nigeria.
Good morning. Welcome, everybody. Good morning to those in Nigeria, and good afternoon to those in Kenya, Rwanda, Tanzania. You're welcome, everybody. You're welcome, welcome, welcome. Welcome to the second class. Last week we had the first class, which was amazing, and today is the second class. So welcome, everybody. So a quick one. Kindly drop a message in the WhatsApp group chat telling your participants to join. Because like I said last week, attendance for this class is very, very, very crucial. You have to be in class because attendance will be taken. And you wouldn't know when attendance will be taken. So as you are joining, also note that you should not leave the classroom. I'm waiting for you guys to send the message to the group.
What message?
Send a message to the group telling your fellow participants to join, that class has started. All right, welcome everybody. Welcome once again to people in Tanzania and Kenya. Jambo, you're welcome. To our people in Rwanda, Muraho, you're welcome. I hope I'm correct. You're welcome. So welcome everybody. Please drop a message telling your fellow participants to join. Class has started. And attendance is very, 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 very crucial. So join in, everybody. Join in, everybody. Join. All right. So what can, just quickly remind me of our topic in the last class? Anybody? To remind me of our topic in the last class, or should I call anybody? No, I'm asking. Please, when you are joining, join with your name, because I'm seeing some people, it is their phone name that is showing, Samsung, iPhone. Please join typing in your name, because that's what will be used for attendance. If it is the name of your phone that is showing, that means you are not in class. So please, you can leave the call, join in again, and put in your name. So as I was saying, who can remind me of the topic of our last class? Hello? Who can remind me of the topic of our last class? Should I call anybody? Yeah. Because you said you didn't send to him. And said energy economics and load analytics. All right. Yes, that is correct, but I need it to be precisely how it words in our material. Who can remind me of the precise word? These are the things that will make us to know that you are actually learning and you are always active in class. I think I'll have to call someone because it seems like we don't want to speak. Okay, Dennis, you can go ahead and speak.
Hello.
Yeah, thank you very much. Okay, one of the topics says that energy is data. So, and that how is energy data? Energy with the information we have concerning our energy usage, we can better plan or design an efficient system that can cater for our energy needs. So, yeah.
Okay, so who can remind me of the eggs? That's correct, but like I said, I need the exact way it was in our material. Should I call anybody, or who else wants to try? Is there anybody else that wants to try? Okay, Engineer Levi, can go ahead.
Hello, good afternoon.
Kelvin, you can speak.
Okay, what we learned in our previous class was about we did about energy, economic, and load analysis,
Okay, cool.
where we learn about energy, what is energy, about data, diesel economics, the issues about the capacity utilization factor, and so many. We did learn a lot of so things. Okay.
Alright. That's nice. That's nice. It shows that we have people that are learning. It's a good thing. Okay, so last week's topic was grid versus diesel economics. And that boils down to a lot of things that we okay, so I hope all of us have been able to do our assignments. Please, if you have not been able to do your assignments, just raise up your hand, please. You can just use the raise up your hand. For the people that have not been able to do their assignments, just raise up your hands so we know. There's nothing to be shy about, though. Just raise up your hands so we know. Okay, okay, okay. Okay, it seems like a lot of people hasn't done their assignment. What's going on? Is it that it's difficult, or you can't find the assignments, or I don't know, tell us what's going on. Ashley, can you speak? Why has the assignment not been done?
Okay, it was a bit challenging. I did it, but now I haven't been able to submit.
Okay, you haven't submitted yet, but you have done it?
Yes, I'm yet to submit.
Okay, please do submit, because assignment is very, very, these are things that will, determine each one of you getting your certificates, because it will be a accumulated score, your attendance in class, your assignments, your projects, and so many other things. All right, so please and please just try to submit today, because I think is today? Sorry, has the assignment's been closed already? Oh, Nessie, you joined late. Okay, it's not a problem. Just make sure you do other assignments as well. Okay, last question before I hand over to the facilitator for today. Who can tell me the full meaning of CUF? CUF.
Hello. Capacity
Yes.
utilization factor.
What did you say?
CUF, capacity utilization factor.
Okay, thank you. But I can see that you're joining with iPhone 14 Pro. Please, you have to change it to your name because of attendance. All right,
Okay.
thank you. That's very much correct. Thank you so much. All right, so once again, the person that will be taking us once again for this week is our facilitator for last week. Engineer Emmanuel, once again, is here to take us today's topic. And just for all of us to note, the course outline will be shared in the Google Classroom before the end of today, so that you'll be able to know the topics that you'll be learning for each week, so that you can also do some learning on your own and then add to your learning year. All right. So thank you very much. So please let us use our emojis and make welcome Engineer Emmanuel. But please note, do not leave the call. Even if you are not fully active, stay on the call, because you don't know when attendance will be taken, and it is very, very important. Also, if you have not dropped a message on the chat on the WhatsApp group, please drop a message telling your fellow participants to join in. So please let us use our emojis and make welcome our facilitator for today, Engineer Emmanuel Adewumi, for another insightful class session. Thank you, thank you, thank you, thank you, thank you, thank you. Thank you so much. You're welcome, sir.
Thank you so much. I really appreciate you. And once again, I welcome every one of you to the Energy Management Cohort 2. And I've listened to some of your contributions early just now, when the cohort coordinator was asking what we learned last week. And I want to appreciate one thing: our cooperation, our excitement to respond, participation, not just that you are present in the class, but you are also present to participate in everything we are doing. I also want to welcome those who are joining us for the very first time. If you are joining us for the first time, I want you to be rest assured that you have not missed at all, because our class will be starting very much proper today, and the lesson would also commence proper today as well. Like we did last week, I would really, really covet your full participation. And don't forget the rule. The rule these days: I am just here to facilitate the class, but everyone is learning together. I'll be presenting the slides for the course. We would have volunteers to read, then another person or other people would share their own insights of whatsoever was read. So that's how we are still going to be doing it. So when someone reads, another person shares insights. And when you want to do that, you just have to use your emoji to raise your hand so that you can be asked to speak. So thank you very much once again. You are welcome to the class this morning. All right, so I'll be presenting or sharing my screen now. I believe you can see my screen. Can you see my screen? Sorry, is my screen visible?
Not yet.
No, it's blank.
No, not yet, not yet.
Okay.
Not yet.
Visible.
Not yet, we can't see it.
Okay. Okay, let me share the entire screen. How about now?
Nothing is showing.
It's showing now.
Okay, it's showing now.
Okay.
I can see the screen.
It's
Bravo. That's good. All right, thank you
showing.
very much. Okay, so once again, we are welcome to today's class. And for today, we are going to be studying a very, 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 very important topic: the energy cost breakdown. The energy cost breakdown. And we are going to be learning a lot about energy costs, what it takes to produce a kilowatt hour of electricity, or let's say a kilowatt hour of energy, whichever way you want to put it. Or let's just say what it takes to produce kWh, right? All right. So before we commence, I would just want someone to, or two persons to just share with us what you understand by the energy costs. Energy costs. Just tell us something about energy costs. Yes. You can just share any insight you have. Please feel free to raise your hand if you want to speak.
Hello everyone, good morning. So when it comes to energy cost, it's all about the amount expended in the cost of generating 1 kilowatt hour of energy. So what that means is, as we know, energy is, for you to get an energy, it's power multiplied by time to get one. But then if I'm running a diesel generator, for an instance,
We can't hear you anymore. Are you still
then
speaking?
how
We
much
can't
am
hear
I
you.
spending so that I will not be at loss? Thank you.
Okay. All right. Thank you. Let's have Gideon.
So energy, the total amount of the total amount involved in generating, transmitting, and distributing energy. Apart from this generating, transmitting, and distribution of energy, operators, the regulatory bodies, so that is factored into the total energy cost. Even the losses that is the losses along the generation, transmission, and distribution is factored into the cost of energy.
All right. Thank you very much. Okay. Let me ask a question that would make me give or assign bonus to somebody. The question is this. We have different sources of electricity or power generation. Now, what is that one factor? There is a particular factor that helps us compare the costs that should be billed or the cost of generating a kilowatt hour of electricity. What factor is that? Does anyone have the idea? If you don't know it, there's no problem. Okay, Abraham, Josiah, unmute yourself.
Okay, good morning. Can you hear me?
Good morning.
Yes, I think that one factor is that should be the fuel you use. That is either it is hydro or steam or gas.
All right. Okay, thank you. Yes.
You're welcome.
Aja Iyom.
Good morning, everybody.
Good morning.
The cost of producing energy will be tied to the fuel used and also the maintenance cost
All right.
of the
Thank you very
plant.
much. Thank you. Let me have Francis Adekunle.
I think it should be the capacity utilization factor because it's how efficient your system is being used that will determine
Okay.
how expensive
Thank
or
you.
how cheap
Thank you. One
your
last person. Akifewa Ajekwe.
Good morning, everybody.
Good morning.
The I think it's the fuel and the resources costs.
Okay, thank you. I
Then
think I have one, please. enough of the hands. Let me just give room to Emmanuel. No room. Unmute yourself.
Good morning, everybody.
Good morning.
By using renewable energy, such as solar.
Okay. All right. Thank you very much. In order not to waste our time, many of you have spoken. You spoke well, right? But you have broken it down than what I expected. You know, I was only asking for a factor. There is a name given to that factor. Some of you mentioned cost of producing the electricity, the fuel used, the capacity utilization factor. You mentioned a whole lot of things that are integrated in that factor that I just want you to mention. So, but let's look at our study for today. We are all going to know what that factor is. So let's pay maximum attention so that when we get there, you can know that this is that factor that I was asking about. All right. So let's move on to our first slide. The nature of modern utility billing. The nature of modern utility billing. So Abraham Josiah, kindly unmute yourself and read. Please unmute yourself and read.
Okay, energy consumption.
Go ahead.
Oh, sorry about that. I am at work, so I have to look for a quiet place.
Okay.
Okay, in the realm of energy management, many facility owners mistakenly view their electricity bill as a simple total for units consumed. However, the modern utility bill is a complex document that reveals the efficiency of an entire operation. For large consumers in Nigeria, Kenya, or Rwanda, the bill is divided into two primary categories. That's energy, and then we have a kilowatt hour in bracket, which represents the volume of work done, and demand, that is kilowatt all over kilovolt amperes in bracket, which represents the maximum speed at which energy was drawn during a specific window, usually 15 to 30 minutes. Demand charge. The demand charge is particularly significant because it is often looked in. For instance, if a factory in Lagos starts all its heavy machinery simultaneously at 8 a.m., it creates a massive spike in the grid. Even if those machines only run for 20 minutes, the utility company, such as EKEDC, that's a co-distribution company, may bill the customer for that peak level for the entire month. This is because the utility must maintain transformers and wires large enough to handle that specific peak, even if it only happens once.
Thank you very much. All right. So
you're welcome.
for us to discuss this slide, I believe we were following. So we just want volunteers to raise their hands to answer this question and buttress their points with some explanations. Okay, let's have people speaking now. I believe we understood what was read. You can look at the question. I'll take it back if need be. I want volunteers to raise their hand before I start calling. You know, I love to call people's name. All right, Dennis, unmute yourself. Go
Okay,
ahead.
sorry, I just wanted you to take it back. I didn't get it well.
Okay. So just
Take
look at the
it back to
questions.
the
Please look at the questions.
lesson.
How do many facility owners view their bills? And why is this a mistake? Then the second question is, what is the difference between energy, kWh, and demand, kW/kVA? And last question is, why does a 20-minute spike in usage affect the cost of the entire month? All right, I'm taking it back now. So you can go ahead if you want to speak. I was seeing some hands already, but I don't know why the hands are no longer there. All right, Captain.
Yes, good afternoon, sir.
Well, thank you. Good afternoon.
Yes. So he said that there's a question 2 here. It says what is the difference between the energy kilowatt hour and demand kilowatt and kVA? Hello?
Go ahead, thank you. Or is it
Yes,
my
so I just
network?
wanted to state the difference there. So for kilowatt hour, this is the total volume of electricity consumed over a period of time. As for the kilowatt,
Okay.
this is the rate at which energy is used at a single moment.
Yeah.
Then the kVA, that
Yeah.
is the total
Yeah.
electricity capacity the utility must supply, accounting for inefficiencies like power factor.
Okay. Thank you very much. I think you have
Yes, sir, that's
spoken
my
well. Yes.
yes, sir.
Do you
That's
have
my
any other
contribution.
person that wants to? Thank you. Thank you for your contribution. Any other contributor? Yes, I need more hands. Yes, Francis Adekunle, can you unmute yourself?
So for the first question, it says how do many facility owners view their bills? I think they view it as the same total unit consumed by the facility over the period of time. That's how they view it.
And how is it a mistake?
It's a mistake because of over time there's the total unit used does not really tell the picture of what is or what is there have to be this total holistic view of how the energy is being supplied at each moment, because there are peak period and at every moment the peak period must be, you must be able to make provision for the peak period at all times, because if you get to the peak period and there's not enough supply for that peak period, then there will be a failure in the system. So that peak period must be supplied, whether you are in peak period or off peak period. There must be provision for that peak period to be met at all times.
Thank you very much. He has mentioned a very valid point, talking about peak period. All right, let's hear from Gideon.
Okay, so the first question, how do facilities owners view their bills and why is this a mistake? So I think most facilities owners only view the kilowatt hour. We don't actually check the demand. Even if you look at the bill given to the customers, you only see the kilowatt hour. The demand is usually not there. But as pointed out by the presentation just now, we have to look at both of them. What's the difference between energy and demand? So it said energy is what is used to do work, what is drawn by the company but for a particular period of time, usually hours, can even go towards days, months. Why demand? Kilowatt hour over kVA. That is apparent power over, that is for power factor. So that's the difference between that. So why does, then the third question. So I think peak period is where they can get a lot of money. So that is why most of the the discos use that for billing.
Okay, thank you very much. Thank you very much. Thank you very much for all your contributions. it is important we view our energy billing correctly. There are times that you need to consider the demand of a particular site so that you can make a maximum profit. Otherwise, if you just bill in the terms of KWH alone, you might be making a mistake. All right, I want us to move on to the next slide now. The power triangle and system efficiency. All right, I would like to call on Emmanuel Urem. Emmanuel, I saw your hand just now. Please take this slide for us.
Okay, I read the power triangle. To understand why a bill might be unexpectedly high, we must examine the power triangle. This consists of real power, P in kilowatts, reactive power, Q in kVAR, and apparent power, X in kVA. Real power is the useful energy that turns motors. Reactive power is non-working energy needed to maintain magnetic field. Apparent power is the total sum of both. We can illustrate this with a glass of beer. The liquid is the real power we want, while the foam is the reactive power that takes up space but does not quench thirst. The ratio between real power and apparent power is known as the power factor, bracket PF. A power factor of 1.0 is perfect, meaning there is no foam. However, if a factory has a PF of 0.70, it means 30% of the energy being supplied is wasted as foam. Utility companies fine or surcharge customers for a low PF because this wasted energy clogs the grid wires and transformers, preventing the utility from serving other customers effectively.
Right, thank you very much. Now, this particular slide interests me personally. So I want us to leave this slide if there is no enough contribution, because we need to understand this, especially this term called power factor. A lot of people neglect it. A lot of people don't even know what power factor means. And it's very important for us to understand what it means so that maybe you find yourself in an electricity division company or an energy management company or facility that you manage. You'd always consider the term power factor. All right, so let's have contributors now. I won't even go to the questions. Let's just share. Let's discuss. Yes, Josiah. Let's discuss. Power triangle, power factor. Abraham, Josiah, unmute yourself.
Okay, thank you for having me. Good morning once again. Talking about this power factor, like we've read, saying it is the ratio of real power all over apparent power. What I want to say is that the greater the power factor of a system, the better it is for that system. Like we've read that for a unit to be perfect, it has to attain a power factor of 1, which is somehow impossible. A unit or a system hardly attains that 1 power factor. That's one point. Another thing, most of us used to actually say that reactive power is useless. Okay, in the real sense, it is not actually useless power, because this reactive power we used to hear about all the time, it is actually used. One of its uses is that it's being used to improve the system voltage. We can say it is being used to increase the system or grid voltage. Yeah, so that's one very important use of the reactive power. I think that's my contribution for now. Thank you.
All right, thank you very much. Yes, let's have Fred Omolo. Fred,
Yes, sir.
go ahead.
Power factor is actually a figure which shows how facilities efficiently using electrical energy, which is being supplied by the utility company. Majorly, when the power factor is lower, you do have some surcharges which is being imposed by your utility company because you are putting more stress on their generating devices like transformers and generators. So this poor power factor is majorly caused by inductive loads like industrial arc furnaces, induction motors. So you need to minimize reactive power in the system caused by those inductive loads as much as they are being required by those loads. You need to minimize them by bringing in some devices to improve on it so that it approaches one to minimize losses in the system.
All right, thank you very much. Now, let's look at typical example. What actually cause a low power factor? What cause a low power factor? Engineer Levi.
Anyway, I had wanted to ask a question, but most times low power factor is actually this is my thoughts. Most times low power factor is caused by inductive loads most of the times. So when the inductive loads are much in the system, stress is induced in the system, and power factor can be a little bit low. You know, to that effect, most times if there is
Thank you very much. We'll give you opportunity to ask a question. But before that, can any other person give us an example of inductive load? An example of inductive load. Someone else? Kabira, can you speak to yourself? I don't know if I pronounce your name properly. Kabira.
Hello? Yes.
All right, I hear you.
Can you repeat the question?
Can you tell us an example of inductive load?
Inductive?
Yes.
Inductive load is like that of motor.
What? I can't hear you.
Hello?
Okay, is there any person speaking?
It's like inductive load. Inductive load is that load from an equipment which use coil, like a motor.
Okay. Yes, Dennis, unmute yourself.
Okay,
Thank
an
you.
example of an inductive load is I would say a grinding machine. A grinding machine.
Okay. Yeah. All right. Thank you very much. Let's go back to Engineer Levi. He has a question.
Yeah, so the question I want to ask is it's this thing. If from your analysis, when you try to describe power factor, that's you try to describe the power triangle. So you mentioned that the VAR is like load, wasted load. So why the system is the real power? Now I want to ask most times in billing, when you want to bill for energy used, how do you bill for the VAR? Because most of these inductive loads, because there are some companies that most times we have this complaint most of the times that this company, maybe a steel company, is generating, while the distribution company is saying, the load that these people are being used, they cannot easily meter it because it's VAR. How then do they now come up with the right billing? How do you now bill VAR? Because it's actually a load on its own, but we see it as kind of a load that is wasted or causes stress to the system. But then how then do you effectively bill that VAR? That's actually what I want to ask.
Thank you very much. I'm so excited that we have people from other countries here. And Nigeria, for instance, we have a standard of billing, system. For those of you in Rwanda and Kenya, you also have standard for billing system. So I would just love to get a contribution from some people from different parts of wherever you are joining us to respond to that question. Yes, I want answers. How do we bill correctly if we say that VAR is a wasted or how did he put it? A load that is not useful. So I want contributions from as much people as possible. All right. Okay, I can see a name here, Mr. Charles. Please, I want to see hands up. Okay, in the absence of none, I would just give us an instance of Nigerian situation. For Nigeria situation, irrespective of your load, whether inductive load or non-inductive load, as long as your meters, your energy meters passes the standard body that certifies energy meters, you are billed in terms of KWH. That's how you are billed. And you know, in the meter already has the fact that it uses the multiplying factors it uses to estimate or to calculate your KWH. Now, but in the situation where you now use an inductive load and maybe an inspection was carried out on your meter and it was discovered that your power factor is below the acceptable threshold. For instance, in Nigeria, the acceptable threshold for power factor is between 0.85, I think, 0.85 to 0.9 or 0.99. But if your power factor is below 0.8, let's say 0.7, 0.75, it's already going to be to flag your meter. That's your energy meter. Because of your inductive load. In that situation, your demand, your KVA would be put into consideration in order to bill you correctly. Why? Because if we use what your meter is giving to us or is showing us, we are going to be under billing you because your power factor is below the threshold. And I believe you all know, and even if you don't know, you know that one of the factors that makes up your KWA that you are used to bill on your meter is the PF, power factor. So when you see that the power factor is below the threshold, is below 0.8, you are no longer going to be billed with that meter again. They will now begin to consider your demand for that month, and it's going to be the highest, your peak demand that would be considered in that situation. So that's why power factor is very, very important. Now, you can just do a rough calculation. You can do a rough calculation to understand the importance of this power factor. The formula for energy is IV times time, right? Times your power factor. Please, you can just note something down. For a three-phase system, the current times the voltage times the √3 times √3 times what now? The time. multiplied by your power factor. Now, just put in any value, and the only thing I want you to change is the power factor. Use, for the values you are using, for your current, voltage, and you can exclude time. For the values you are using for your current and voltage, at one point, use 0.7. And at another point, still with the same value, use 0.9. Then you see the difference. So if we use the meter that is giving us 0.7 or 0.75, and then we use your neighbor's meter that is showing a value of power of 0.9, who is at the losing end? You realize that we are cheating your neighbor whose meter is displaying correctly, who is not using an inductive load. So that is why power factor is very, 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 very important when billing is happening. So whenever a meter is showing a power factor below that threshold, we no longer bill you with your energy meter anymore. I don't know, and I hope that what I've said answers your question already. Thank you very much. Let's move on to part 3. I want hands up now, volunteers to read for us. Thank you, Mercy. Mercy, please unmute yourself.
Good afternoon from Kenya.
Thank you,
The way
Kenya.
you are speaking was like you are using the services that are payment billing that is used after maybe a monthly, that they come and check the meters and see, or is it that it can also affect for people like for us, we usually pay, there's a prepay service. How do we factor in that one?
Good. Now, thank you very much. I was thinking you want to read for us. For those that
I can also read.
For those who use prepaid services, right? I don't know how it is in Kenya. From time to time, we have those we call commercial officers whom goes for periodic check. Sometimes the prepaid meter can also develop issue, or even internally, someone may be using an inductive load. If they come at any time and realize that your prepaid meter also is giving a wrong value, it should on a normal ground be flagged. It should be flagged. But now you realize that most people who use inductive load cannot use a prepaid meter. For instance, if you have a factory, you can't give a 3-phase prepaid meter for a factory. But there is a meter we call in Nigeria maximum demand meter. They are MD meters. We have them in the rating of 100 amps and above. We have 100 amps by 5, 200 amps by 5. Why? Because their load already exceeds what a simple prepaid meter can accommodate. So these are the people who use inductive load majorly. But for them, you can't use a prepaid. So you have to give them a postpaid system so that you can also monitor their consumption. You can monitor the performance of their energy meter as well. I don't know if Mercy understands this explanation.
Yes, I get it.
Do you understand? All right,
Yes.
Thank you very much. So
I can
you
read.
please read the rules, the threat of harmonics and transformer losses.
Okay. The threat of harmonics and transformer losses. Harmonics, beyond the power factor, a silent threat known as harmonics often exists within a facility's electrical system. Harmonics are electrical pollution created by modern devices like LED lights or variable frequency drives. Instead of clean, smooth wave of electricity, harmonics create jagged, high-frequency noise. The noise causes transformers to vibrate and overheat, and it can even cause the neutral wires in building to catch fire. Transformer losses. Further, large facility above 300 kVA are often referred to the primary side, the higher voltage side of the transformer. That means the customer is led for transformer losses. Even when no machines are running, the transformer itself consumes energy to maintain its internal magnetic field. And an alert energy manager knows that these no load losses can cost a company millions of naira or shillings every year if not monitored.
Right. Thank you very much. Now we need contributors now. Share your insights based on your understanding. Yes, I want to see hands. Share insights based on understanding. Thank you. Thank you. I can't see hands. Even if it is to speak about transformer losses, please unmute yourself and speak. All right, let me call, call Leslie. I know you read for us, but do you have any insights to share based on what you read? Is Messi still there? We are the engineers in the room. All right, I can see one hand. Please, Engineer Levi has always been speaking. All right, go ahead, unmute yourself and read. And speak, share insights. Sorry.
So from my own end, this is actually insight. This is just me having a different view. Like I just understood something clear. So on harmonics, in as much as we've been talking about harmonics, I really have not thought of the billing. I really don't know that facilities or these guys, the LED lights and all of that, they actually affect the transformer. Yeah, I've not actually thought of this, honestly speaking, because most times we just feel we just install our LED lights and they are beautiful and a whole lot of them and all of that. But I don't know that they affect or increase the losses of the transformer. And most times when transformer hums, as we know that it hums and vibrates, to us we just take it that's magneturiction as they always we've always known, but I really don't know. I'm just seeing this as an eye opener, and that's quite interesting. So, what I want to now ask you: so, does it mean that the distribution companies that they would come assess the quantity or the kind of load that you have that will result to harmonics and all of that before they also determine the kind of energy meter they are supposed to also give you?
Okay, thank you. Yes, we'll get to your question. Murigi. Sorry, I can't pronounce your name. Omit yourself. And Charlotte Murigi. Please omit yourself. You can help me pronounce your name clearly. Your hand is still raised. Murigi and Charlotte. Okay. Can we have another person? Yes, go ahead. Mercy, okay. Mercy, please go ahead and speak.
Okay, thank you so much. I'd just like to maybe elaborate regarding transformer losses. Transformer losses In this text, we are told that large facilities like industries which are supplied or metered are actually metered at the primary side. That is transformers above or the demand by the customer above 300 kVA are metered at the primary side, unlike the small scale, in quotes, customers who are not who are metered at the low voltage side, actually at the service at the end of the service cable, and they are billed for the transformer losses. Such that even when there are no machines running for that particular customer, we normally refer to them as the large power customers. They'll still be charged because the transformer itself, when it is just installed there, it consumes a lot of energy, even if there are no loads. That is what we call the no load losses, and it can cost a company a lot of money. Thank you.
Thank you very, very, very much. Do you work in Kenya Power?
Yes, please.
Mercy. Huh?
Yes, please. I work there.
I caught you. I caught Mercy. That's good. All right. Okay, let's have Charles and Naya.
Thank you very much for having me here. Actually, I've been trying to handle between work and the classes as well. But then, some of as an energy enthusiast, I'm trying to kind of I'm trying to kind of a new career, and some of the times they are quite so. That's why I'm actually trying to also to learn on the background. But for a quick one, from my understanding from the notes I've read so far on the screen here, I don't know if anyone is hearing me. Is anyone hearing me?
Yes.
Okay.
Speak.
Okay. Okay. So from the harmonic aspects, coming from the part 3 of the threat of harmonic and transformer losses, I want to share my insights regarding the harmonic effect, the harmonics affecting transformers. And that is where when a transformer feed harmonic reach load itself suffer. So, and where it suffers is the extra heating, and the extra heating is the eddy current and the losses in the core rise faster than the fundamental current alone will suggest, because losses scales with the square of frequency for some components. Then another one I also want to share about the reduced usable capacity and the natural conductor overload. That is just little I can contribute, like on the inside concerning the harmonic. Thank you.
Thank you so much. Thank you, Mercy. All right. So if you look at the text, you see that it was said that it is a silent threat. It is a silent threat. So you can be using a LED light. I'm trying to answer the question that one of us asked. You can be using a LED light in your house. That may not be, something that will really, really affect the distribution company in any way that will make them to come and monitor whether you use LED lights or not. No. Why? Because it is a silent threat. It can cause some threats. However, we need to consider more the transformer aspects. Now, one of the major reasons why distribution company, for instance, would meter, for instance, if you have a transformer they would want to meter at the primary side before their supply even reaches your transformer at all. They want to know all that is entering, all that your transformer is receiving from the primary side. That's before the transformer on the high voltage side. The reason is this: many of us, when you go near a transformer, for instance, you hear some humming sound. It keeps on making some sounds, and then you know, apart from that, by the time you now send supply from your transformer on the lines to wherever you are taking the power to, you also have what we call line losses, technical losses. So before all those things start happening, they want to meter and be sure that everything is captured. The reason being that all those humming sound and the technical and line losses, they all result into losses for the distribution company if not properly metered. So whether harmonics or transformer losses, they need to be properly monitored in order to save costs on energy production. I would believe that the person who asked the question has received answer to his question. I want to move on to part 4 of this class. But by the way, some of you would be wondering, how did I catch Mercy to be working in where she has mentioned? When you talk, I might be able to discern what or where some of you are working or what you are currently doing because of the way you would respond, especially those of you who are working in a facility or energy-related industry. All right. Okay, let's move on to part 4. Part 4 is strategic solutions for the energy manager. Dennis, please unmute yourself and read.
Strategic solutions for the energy manager. So the role of an energy manager. The role of a successful energy manager details to save the company money. By installing capacitor banks, they can eliminate power factor penalties. They can shave the demand peak. In countries like Kenya, they can use time of use, TOU, time of use strategies to move heavy production to the night hours when rates are 50% cheaper. Energy management. Energy management is about more than just turning off lights. It's a high-stakes financial strategy. By mastering the math of timing of the grid, a manager transforms a facility from a source of waste into a model of efficiency. This but also extends the life of expensive equipment and contributes to the stability of the national grid.
Thank you very much. I hope we all are followers. I would volunteers to respond to these questions based on what has been read. List 3 technical solutions an energy manager can use to reduce costs. How does time of use help a factory save money? And the last is, why is the energy manager's role described as a high-stakes financial strategy? Yes, volunteers now, share your insights based on what we have read and answer the questions for us. Okay, can I call on Francis? 3 Francis here, right? Okay, someone has raised his hand. I wanted to call Francis Akibe. Francis Akibe. Emmanuel, let me come back to you. Francis Akibe, let me see if you are following us. Francis, are you there? All right. Emmanuel, please go ahead.
All right. I'll be taking the first question, which is three technical solutions an energy manager can use to reduce costs. I think from the previous slide, we saw that the energy manager can employ the use of capacitor banks. So an energy manager can advise a company to purchase an appropriately sized capacitor bank, which will aid in improving the power factor, minimizing the power factor losses, soft starters, which will help in saving power when starting inductive devices such as motors, which have a lot of high starting torque. And then also with the TOU, the time of use, which will help the company to move their more energy hungry operations to hours where they will actually be charged less. So it's the other question was also talking about how it's a strategic or high stakes financial strategy. It's that the energy manager is not just concerned about observing the power usage and the consumptions, but they're also concerned with how they can employ strategies and tactics to mitigate the losses and also save the business as much money as possible. Thank you very much.
Okay. Yeah, thank you so much. Thank you so much. And I need someone to just answer the last question for us. This has taken care of. This has taken care of. This for us. Yes, thank you. Is anyone speaking? Okay, go ahead. Go ahead.
Kindly the question, the screen, I'm not seeing it well. You can expand it so that I can be able to see the writings. Thank you.
Okay, Noel, please unmute yourself.
Okay, good afternoon. I would like to add on why is the energy manager's role described as a high stakes financial strategy in a way that when it's an energy manager's role, when he's consulted by a company to install or to take charge of the energy sector, he is going to advise the company on from the previous slide. We are told that the TOUs, they are to move the heavy production to the night hours. As the company management may not know that the billing systems are lower during the night hours, but the energy manager will know of that. So he will advise accordingly that the heavy working or heavy machines can be readjusted to the nights, while the lighter ones can be readjusted during the day so that the cost is also reduced. Thank you.
Thank you very much. Yes, do we have someone else? I can see Murigi again. You have raised your hand the other time, but you didn't speak. Do you want to speak? Please unmute yourself.
Hello, good afternoon.
Good afternoon. Go ahead.
Yes, I just wanted to add on the last one here. Why is our energy manager role described as a high stakes financial strategy? Yes, so I'm going to speaking on the capital allocation. So, like decisions, decisions involve substantial upfront capital and expenditure on technologies like solar power.
Yeah.
So waste heat recovery or automated controls. So incorrect focusing of this or poor implementation risks the capital. So while successful strategies deliver a strong payback period and long-term cost containment against volatile tariff increases for an organization. So like this rover the energy, once it's a high stakes because it involves a lot of technical analysis. So you have to be, it's, I don't know how I can put it in really, but I'm sure you've understood how I've tried to explain it.
Okay, thank you very much. Can I have Morigi again? I know you wanted to speak earlier. Please, kindly unmute yourself and speak.
Can you hear me?
Yeah, I can hear you.
I wanted to speak about the role. Why is the energy manager's role described as a high-stakes financial strategy?
Okay.
This is basically because the decisions directly affect how much money a factory spends on energy. This can range from reducing electricity and fuel costs, choosing the best times to use energy, as the previous lady has indicated, in terms of, like, for instance, in Kenya, whereby you use TOU to know the peak hours, off-peak hours, and mid-peak hours. Also, the energy manager can identify energy waste and improve efficiencies in our operations, let's say in a factory. They can also make investment decisions about energy saving equipment, like, for instance, VFDs, which can be used to reduce harmonics. Yeah, that's all from me.
Yeah, perfect. Thank you very much. Thank you, every one of you. You have spoken well. And I think since most of you were just contributing on the side of energy managers role, maybe there are some who would want to take the energy managers certification program among you. I think you will be able to save a lot of money for your organization or any organization you'll be joining later in future. Okay, all right. Let's move on to the next slide for today. Let's move on to the next slide. The math of peak shaving and load factors. The math of peak shavings and load factors. Now, I can notice that we were initially at 109 participants, but the numbers is reducing to 98 now. Don't forget, I asked a question when we started. I know you don't want to you don't want to miss that answer because I've not given answer to it. There is a factor that helps you determine the price or the cost of kilowatt energy of electricity for different kinds of sources. Make sure you wait till the end so that you can get that answer. Thank you. So I want someone should just volunteer to read part 5 for us, the math of peak shaving and load factors. Yes, thank you, Murigi. You can go ahead and read.
So for the load factor, to effectively manage cost, one must master the load factor. This is a ratio that shows how flat your energy usage is above time. A high load factor means you are using a consistent amount of power, while a low load factor means you have high expensive peaks but low average usage. The formula is load factor equals to actual kilowatt hours used in the month multiplied by peak kW times 720. Should I
Go
proceed
ahead.
to the next? Peak
Please
shaving.
proceed.
So for peak shaving, consider a factory in Nairobi. If they use 100,000 kilowatt hours in a month and their peak demand is 400 kilowatts, their load factor is 100,000 divided by 400 times 720, which equals to 0.3, which is 34%. If they use peak shaving turning off non-essential loads when the main machines are on to drop their peak to 250 kilowatts. Kilowatts. Their load factor improves to 0.55, which is 55%. This simple shift saves millions in demand charges without reducing production output.
All right. Thank you very much. Thank you so much. Let's have contribution from the questions we have here. What does the load factor represent? And the second question is, based on the formula in paragraph 9, what happens to the load factor in the peak KW increases, if the peak KW increases? Yes. Let's have contributors now. Let's have contributors. Yes. I can't see hands yet. All right. I'm going to call on Chibueke Okpara. Can you unmute yourself and speak? Chibueke Okpara. Chibueke Okpara. Yes. Please, even though I'm calling on people, you can still volunteer to answer the question. I will go back to the slide so that you can see. We want contribution. We want you to share your insights. Yes, who is speaking? Abdul Kadir. Abdul Kadir Sada. Nobody is responding. It seems okay. Maybe some of you are at work. Okay. If you are in a place where you can't speak, you can also write a text. Okay. Someone said is in the office. Yes. Please speak if you can speak. Unmute yourself if you can. Lewis, can you unmute yourself to speak? Right. Manuel, kindly volunteer yourself. Okay, thank you very much. You go to.
Sorry, I can go ahead.
Yes, go ahead, please.
Oh, okay. Yes, so the two questions are talking about what the load factor represents and what the peak kilowatt increasing would do to the formula. So the load factor represents how much money you're going to have to pay, or rather, if your operations include a peak power usage while you have a very average low usage throughout the month, then that's actually going to give you a very low load factor. And then if you have a consistent load, then you're going to have a high load factor. So what it actually represents is that if you want a higher load factor at all times, because that's going to mean that your billing is going to be consistent with your actual usage rather than your billing being based off of the times when you have very high loads. And relating to energy management, the goal of the energy manager is always going to be that he wants to maintain a very high load factor. So a high load factor represents a good, consistent usage that does not involve high peaks with low average usage through the month. And then when we talk about the peak kilowatt increasing, what that means to the formula is that the higher the peak kilowatt, then that means that you are going to have a lower load factor. So you're going to try to minimize the peaks as much as possible. And you can do that through different means. The most important one is what the lady had previously mentioned in her contribution, where she talked about using self starters and VFDs to control the surges in those motors as they are operating or as they are starting, so that you keep your peak kilowatts in manageable ranges that aligns with your consistent usage. Yes.
Thank you very much. Thank you so much for doing justice to that. I have Mulenga Chibamba. She said load factor, referring to the utility bill situation, means a load factor may result in increased monthly bills for a facility. All right. So I would just like to say that if you are in a place where you cannot unmute yourself, please, you can also use the chat. I would open the chat so that I can read notes and contributions on the chat as well. Thank you very much. I'll move to the next part. Thermal inertia and ice storage strategy. I'm thinking that the last part, most of you did not respond to that, probably because you don't like mathematics. I don't know if that's true, but I've helped you escape that, so I won't call anybody now. So let's move on to the next slide now. Contributors, who is reading for us? Who is reading for us? Okay. Okay. Noel. I have many hands now. Please, just like I'm having multiple hands, I want multiple insights as well. Multiple people should raise their hand for insights. All right. Thank you. Noel, please go ahead.
Good afternoon. Thermal inertia. On thermal inertia and ice storage strategy. Slide 1, thermal inertia. One of the most exceptional concepts for an energy manager is thermal inertia. This refers to the ability of a building's mass, concrete, water, or air to hold temperature. In Rwanda, a manager can use the building as a battery, but supercooling a hotel to 19 degrees Celsius during the cheap daytime hours. The manager can shut off the chillers during the expensive 6 p.m. peak. Ice thermal storage. This is often taken further with ice thermal storage. A facility uses cheap nighttime electricity to freeze a massive tank of water. During the heat of the day, instead of running an expensive compressor, the facility blows air over the ice to cool the building. The calculation for the cooling capacity Q stored is Q equals to M times LF, where M is the mass of the ice and LF is the latent heat of fusion. This exploits the belly of the dark curve when prices are lowest.
Right. Thank you very much. Thank you very much. So let's move on to sharing insight. Jeremiah, inside afraid.
Pardon? Oh, you're breaking
Okay,
up.
go ahead. Go ahead.
Who?
Is anyone speaking? Please, why are we not responding this time? Is the topic too hard? Is it too hard?
Hello, can you hear me?
Yes, we can hear you.
Okay, sorry, please. Can you come again with your question?
I've not asked a question. I just want you to share insight based on what was read.
Okay. From what I understand, based on what was read, I understand more of the ice thermal storage, whereby in your quest to save cost of energy for maybe your facility or your company, you kind of use you run those your compressors that cools the air during the least peak hours where the electricity cost is very cheap. So during the daytime when the building is hot or maybe the facility is hot, and that's the time where the electricity cost has increased. You now just blow just maybe normal air through the eyes, and then you cool the building. So in turn, you have achieved. Hello? Sorry, are you speaking? Hello? Sorry.
Mm. Go on. No.
Sorry. Someone saying something.
I think the facilitator is having some network challenge. I don't know if he can hear you. Okay, he's muted. Maybe he's muted, something like that. Please let's be patient for him to come back. Hello, peace, are you there?
But let's just
Okay, but
concepts. They both are concepts of managing energy. They are both concepts of managing energy. Let's just understand it that way. All right. And someone has already explained the ice thermal storage concept for us. All right. So without any further delay, I want us to move to the next part. I would like to remind you that there was a question that was asked when we started. Some of you have spoken, you gave some responses, but it's not absolutely correct what many of us said. We are going to be getting that response or the answer to that in part 8. So please make sure you patiently wait. We are almost getting there. Let's take part 7 now, the physics of voltage unbalance, when voltage is not balanced. All right, Mercy, you have read already. Can I have someone else who haven't read today? Noel, you have also read. Okay. Banda, yes. Banda, I don't know if I pronounce your name well, but you haven't spoken at all. Please read.
Good afternoon.
Good afternoon.
Voltage and balance. A silent killer of industrial motors in Africa is voltage unbalance. This occurs when the three phases provided by the utility are not equal. If the voltages are 450 volts, 405 volts, and 395 volts, the average is 405 V. The maximum deviation is 10 V. Unbalance calculation. The percentage of imbalance is calculated as unbalance equals to max deviation over average times 100. A 2.46% unbalance will cause the motor to run much hotter, requiring it to be derated to about 90% of its capacity. Running at full load under these conditions will destroy internal insulation, leading to motor burnout.
Thank you. All right, let's share insights. This is right, especially for those of you who work in the power distribution company or work in a facility, and then sometimes you've heard, oh, what is happening? We have three phases, the red, yellow, and blue. And why are we not having supply on the yellow phase? Why are we having no voltage on the, or why is our three-phase system, three-phase equipment not working? Why? What's happening? But there's lights. So let's have contributions now. Jeremiah, Annie, I'm calling you for the second time. Okay, no problem. Go ahead. Juma Azin, are you speaking? Oh, we can't hear you. Please check your audio and you can try again. All right, let someone else speak. All right, go ahead, Jeremiah, Annie.
Okay, so voltage unbalanced, or will I say imbalanced voltage or unbalanced fault, most of the time as it's popularly known, it's a scenario where you have a three phase input and you notice, let's assume maybe in Nigeria we are supposed to be getting, for example, maybe 220 volts, and then you notice some of the phases are experiencing low voltage, whereby the voltage across those phases are kind of not equal to the remaining ones. So it sets up an unbalanced fault. And when you run electrical machines which run on these phases, if we understand the unbalanced calculation, it most of the time affects the internal workings of these machines, whereby making them to overheat and maybe even destroying or spoiling the coils inside as a result of this unbalanced fault coming in. And most of the time, like places in Nigeria, when you experience this, you see some buildings switching from one phase to another, in turn overloading those phases that are working. Maybe one phase is okay and the remaining two phases are experiencing this unbalanced fault, people overloading the phase which is balanced, and most of the time you experience the cables carrying this particular phase cutting as a result of too much voltage on those particular lines. So this is actually what I understand from my experience in unbalanced fault and voltage unbalance or
All right,
voltage unbalance.
thank you very much. Let's take the first question here. What causes voltage unbalance in a system? Yes, I want another person to share insight for us. Is someone speaking? Please feel free to also share your contribution on the chat page. All right, Engineer Lever, have you speak?
Yeah, so causes of unbalanced voltage in a three-phase system. Basically, it's always faults in the distribution network. Sometimes a jumper may be weak or may cut even, and then you notice that that phase will not be carrying the expected voltage. If you just measure the voltage, it just be very low. So sometimes maybe like due to weak conductors or that's weak conductors, maybe hot conductors. Yeah, this actually affects the voltage and could cause one phase to be experiencing low voltage while the others is experiencing normal voltage.
All right, thank you very much. Let's have Mr. Francis Adekunle. Unmute yourself.
Okay, so for the causes of voltage unbalance in three-phase system, I think one of the major problem is usually the load distribution. If the load are not distributed evenly, then some phase will be drawing more load than the other, which can cause voltage unbalance in the three-phase system. And also, I think the phase angle between each of the phases can also cause, if the phase angle is not, if they're not adequate, because now they're meant to be separated by 120 degrees from each other. If they're not adequately separated, then it can also cause voltage unbalance.
Thank you. Mr. Dennis.
Okay. If I'm correct, but I think what can also cause it might be the distance, like the function of voltage drop distribution. So the closer a factory is to the distribution, the higher or maybe the more stable. And why, if
All
it
right.
is far away, then it can drop over time.
Thank you. I have a contribution on the chart page on even distribution of single-phase loads, open or high resistance connections. All right, thank you very much. You've all spoken well. All right, now I want to move to part 8 now. This is where the answer to the question that I asked is. I want you to pay attention. In fact, here I want a lot of people, you are into solar or in any kind of renewable energy, you are into conventional energy production or distribution company, whichever. Please pay attention to this because many of us we are not aware of it before. And some of us probably you are aware, but you don't even care. You don't know how to use it. Some of you even have projects, you want to have a solar farm, you want to be able to sell electricity to, to people, maybe shops or neighbors around you, but you don't even know how to come about the costs of the electricity you want to be selling. This is where the answer is. So let's move on to part 8 of our today's study, solar integration and the LCOE reality. LCOE reality. So before we get there, who can tell me the meaning of LCOE? Don't use ChatGPT, Henry Miner. Don't use ChatGPT, don't use any AI. Yes?
LCOE is the unit cost of electricity.
No, that's not the full meaning. It's an acronym. I want the full meaning. Yes?
Levelized cost of electricity.
You say what?
Levelized cost of electricity.
Oh, that's awesome. Thank you very much. That's correct. Levelized cost of electricity. All right. Let's have someone read for us now. Thank you, Chibamba. Okay. Who is reading? Dennis, go ahead, please. Hold on. I saw Amos just now. Hold on, please. I just want someone who have not spoken. Amos have raised down toward his hand. Okay. All right.
Solar PV.
Hello?
Okay,
Hello?
let me read.
All right, go ahead.
Okay, solar PV.
Sorry?
Photovoltaic.
Okay.
So in many African markets, solar PV is a financial necessity. However, a manager must understand the levelized cost of energy versus the utility rate. While solar can drop the energy charge, which is in kilowatt per hour, so the kilowatt hour during the day, it does not automatically reduce the demand charge. That's kVA. So if a cloud passes over a massive array while the factory is at full capacity, the grid must instantly provide that power, creating a new peak. Solar must be paired with smart logic to ensure it reduces both volume and velocity.
Okay. All right. Let's have contribution with the following questions. What is LCOE and why is it important? What is LCOE and why is it important? Here now, I need a lot of hands. I need a lot of response. Please, I want a lot of response. Yes, Dennis.
From the notes that has been read, I think SCOE, which is the levelized cost of electricity, is would I say is what can enable us to know how to cost the energy we are producing or sell to clients. So like it says it's a very between what we are producing or the cost of it itself, the cost of what we are producing, the rate or something.
All right. Thank you very much. Let's have someone else speak. Thank you. Okay, let's have someone else speak. Who is speaking? Why is LCOE important? Please unmute yourself. Oluwafeyikemi Adefemi.
Okay. Good day. So from the slide I was actually read, so LCOE, why it's important, I think like on average, like I think it shows like how much it really costs for like to generate each electricity from the system, right? So I think so basically what the LCOE is saying is like, well, I think why it's important because it just shows us what it actually costs us like to generate power basically from the system, like to compare the sources
Okay,
of the
thank you very much.
yeah. Thank
Thank
you.
you very much. Engineer Levi.
All right. So why LCOE is very important is that, for instance, for solar in a solar system, you should be able to understand that these guys they have life cycle. Over time, it may last for about 10 years, 15 years, 20 years, the case may be. So you should be able to know the life cycle, know what is expected of you to build, such that you can be able to recover your money so that you don't go and be shop charging, and then at the end of the day you don't even have money to maintain your facility, or at the end of the day to even recover the money that you are injecting. So that's why LCOE is very important. You know the cost, what you are going to pay, your losses, the life cycle of the equipment you're installing, and a lot of them. So you'll be able to know how much you're going to charge so that you can be able to make money, make profit, and have a turnover and keep your facility running.
Thank you very much. Umar Mohammed, can you unmute yourself? I saw your hand.
Okay, thank you. So, sorry, my own is just an addition from what they said, or maybe complementing. So we need the LCOE to be able to compare other sources of energy and see that whether it's profitable or not. Because if we don't do that, for example, in solar, you see solar has an initial upfront cost, which is very high. So if you only calculate the energy that is produced, maybe at a given instant, you might not be able to understand what it actually costs for the total energy. So you must compare it with the value over a lifetime. So when you levelize the cost of energy, you'll be able to compare with other sources such as diesel and other things and see whether it is worth investing or not. Thank you.
Thank you very much. All right, so on the chat page, I have some contributions. LCOE is levelized cost of electricity. A solar array may fail to reduce demand charge when undersized. Okay, the solar array may fail. So to reduce the demand charge, I don't really get what's the person, but I think the person is trying to say to reduce the demand, you need to charge higher. Okay, LCOE tells where the money is going. With LCOE, you are able to know your spend on per energy source basis, at which point your decision will be data driven. Okay, thank you very much. We have all made very important points. So we have made a very important point. I want us to quickly do a calculation now. All right, you can drop your answer on the chat page. You can drop your answer on the chat page. Suppose a solar plant costs 100 million in your own currency, whatever your currency is. Suppose a solar plant costs 100 million to build. So I'm in Nigeria now, I'm using Naira, okay? Suppose a solar plant costs 100 million Naira to build. And over its lifetime, it generates 2 million kilowatt hour of electricity. Over its lifetime, it generates 2 million kilowatt hour of electricity with total lifetime cost of 120 million. What should be the LCOE? What should be the levelized cost of that electricity? Do we understand the question?
Sorry, please. Sorry, please
Can
come
you
again,
just
sir.
repeat the question, sir?
All right. Suppose a solar plant costs 100 million naira to build over its lifetime, and it generates 2 million kilowatt hour of electricity with total lifetime cost of 120 million naira. What should be the LCOE? What should be the LCOE? Have I told us the formula for LCOE already? Have I told us the formula for LCOE? Okay, I
No,
have
sir.
someone
No,
raising
sir.
his hand. Let me hear from Gideon. Yes. Gideon, can you speak?
Okay. So the LCOE is 110.
How did you calculate it?
So I added the 100 million and 120 million. That is average cost to build and operate the power plant divided by total expected output over its assumed lifetime.
All right. Do we have any other person who want to contest that?
Hello.
Yeah, go ahead.
So I calculated mine in dollars. It's giving me $60,000.
You say what?
So the formula was $60,000. So the formula was the total, which is the total lifetime cost
60.
over the total lifetime electricity generation.
Can you send it on chat? I can't hear you. Okay. Okay, I can see someone saying 16 naira per kilowatt hour. Okay. Okay. Someone say I should type the question.
Yes, so mine gave me, I calculated in kwacha, so it still gave me 60 kwacha per kilowatt hour. Zambian kwacha.
Okay. Okay. All right. Do we have any other person?
I've gotten 64.8 per kilowatt hour.
Okay. All right. I want to appreciate every one of you because especially those of you who said 60 or 64. Those of you who said 60 or 64 are correct. I wish your cohort coordinator has a gift in now. I would have asked her to give everyone who measures 60 or 64 because if we approximate it is 60. Okay. So thank you very much. Those who mentioned 60 are correct. That's it. So I would like to call on the person, if you can speak, among those who said 60, please explain how you calculated it for us. Yes, Mr. Dennis, I think you mentioned
So
60, right?
so that was this is Brighton here. That was 120 million over the 2 million of the total lifetime generated over, that is a total lifetime cost over the total lifetime generated.
Thank you very much. So levelized cost of electricity is simply the lifetime costs all over lifetime generation, lifetime energy generation throughout its lifetime. What's going to, we need to consider, ask the question we started. Some of you were mentioning the type of fuel used, the cost of the fuel used, the for the lifetime cost of electricity, you need to consider the event. You need to also operating because you are paying for the fuel usage. You are going to be operating the system. Please pardon me. Pardon why. Sorry, I'm back. All right. So you need to consider all the costs applicable to the production of your energy, including operating costs. And some of the importance of the LCOE includes, among what we have already said, some of you have mentioned comparing different sources or different technology. That's part of the importance. It also helps you in decision making to know which of these sources or which of these technologies should I invest. You don't just want to invest on anything. Don't just want to invest on solar. You don't just want to invest on wind power. You want to compare. If I invest this amount on wind or I invest this amount on solar or whichever, which one would be more profitable for me? You want to be able to set tariff price for selling a kilowatt hour of electricity as well. That would also help you, and so many more. It also helps you in planning better. So these are part of the importance of understanding LCOE. I don't know, I saw some hands raised before my network disappeared. I don't know if someone still wants to ask question. I think Mercy raised her hand. And okay, Mercy, I know I saw your hand. All right, unmute yourself to ask your question.
So, I asked my question on the chat box as well.
Okay.
So it wasn't clear to me whether the cost
not
of the construction should be included in the.
It's
Yeah.
part of it. It's part
And if
of
it's
it
part,
because yeah, you include capital expenditure
so
as
if
well.
it's part of
Your
it,
cost for construction is yes, it is.
so if it's part of it, then you mentioned
is.
the initial
Every
cost.
cost.
Okay. So initially,
Yes, every cost incurred.
Okay. So my follow-up question is, initially, you mentioned a 100 million to build. Wasn't that supposed to be included in the total of that should be 100 million plus 120 million as part of the total cost? and that will get us to 110.
No. So what we need in that question, questions can be asked to even test if you really understand the what's it called now? The concept. So all you just need is the lifetime costs and the lifetime production.
Mm-hmm.
The lifetime cost is inclusive of all the costs that you have, incurred. That's the lifetime cost.
Okay. Thank you.
Yes. So, if you look at it, the lifetime cost in the question is 120 million, right? The question also says the solar plant costs 100 million. So it can be assumed that 20 million is the operating cost, operation costs.
Okay.
Do you understand now?
Yes, I understand.
Operation costs and the salary paid to the staff, okay, thank you very much for understanding. All right. Yes, Dennis, Mr. Dennis, please omit to answer your question, to ask question.
Sorry, that is what I wanted to
contribute.
ask. I wanted to ask what are the parameters involved in the needs? Thank you very much.
All right. Okay. Do I have any other and any question unanswered? Very close for today. I think it's important for me to show you what is next. Can you see my screen?
Yes.
Yes.
This is a conclusion. The strategic shifts. Optimization is important, and energy mastery. Utility bill is a report card of a facility's health. We have seen is a form of reactive power of harmonics leads to equipment death. This concept proved that energy management is not about deprivation, but about optimization. The goal of week 2 is to move from energy ignorance to energy intelligence. So I believe, especially if there are people among us who wants to become energy manager, you want to have your own solar system, you want to have your own renewable energy production and the rest, you have become more intelligent, especially by understanding LCOE today. By applying forensic math to every line item, from transformer losses to voltage unbalance, we protect profits and infrastructure. Mastery of these principles forms the foundation upon which AI future energy saving measures will be built. Thank you very much for joining this class. I believe that today's class has opened our eyes and we have understood certain things better. I hope to see us again in the next class next week in this number. Thank you very much for joining today.
Thank you very much, sir.
All right.
Nice day.
Please just confirm. Can you all hear me?
Yes, we can hear you.
Yes, yes, we can hear you.
We can hear you.
All right, splendid. Please let us just show appreciation to our instructor for today, Engineer Emmanuel Adeomi. Let's use our emojis. Let's show appreciation, right? Thank you. Thank you. Thank you. Thank you. Please let's do more. Let's do more, please. Thank you. Thank you, everyone. Thank you so much. Nice, splendid.
Thank you. Thank you.
It's not for this week.
Okay, to our people in Nigeria, we say thank you for joining today's class. Our people in Kenya, Zambia, and Rwanda, thank you for joining today's class as well. To those of us that still joined,
hello.
voice.
I'm so sorry for interrupting you. My friend from Kenya who works in the Kenya Power, you can look for one of my good friend also who works with you in Kenya Power. Her name is Lillian Kamanja. Okay, you can let her know that you joined a session held by me if you know her. Okay, thank you very much.
All right, so the person that works in Kenya Power, please let the person know that, let Lillian Kamanja know that you joined a class that was, coordinated by Engineer Emmanuel. Thank you. Thank you so much. Thank you so much. So once again, thank you everybody for joining. Please, if you have not done the assignment, kindly do so because it will be marked. And when it's marked, there will be no room for that. Those of us that are just joining, please, the coordinators, please drop the classroom link, please. Kindly drop the classroom link so that they can join. Please, our cohort leaders here.
Yes, I can hear you. We dropped it.
Okay, Engineer Levi, please drop the link in the chat room now so that they can join the group chat, because that's where information should be getting quicker information on how the course or the course rather goes by. So today is our week 2. Our week 2 has come to an end. We're moving on to week 3, which will be next week. And mind you, it will be a new instructor, and I'm sure you don't want to miss that as well. So thank you everyone for joining. Please, Levi, I'm still waiting for you to drop the group link so that they can join, please. Please drop the group link so they can join the WhatsApp, because I'm sure that there are new people here. Okay, so Levi has dropped the group link, so please make sure you join. Okay, that's for the Google Classroom. The WhatsApp group link, I mean, please. The WhatsApp group link, please. Okay, thank you. So he has dropped the WhatsApp group link. So please join. If you know you're not on the WhatsApp, please join so that we are begging now, because there will be a time that we will not beg. So please join the WhatsApp group chat. Thank you, everybody. Thank you.
Just a quick question, madam.
Okay, please make it quick.
Yes, sorry, I just wanted to know, is there any assignments that are going to be allocated concerning this lesson that we had?
Okay, so thank you so much for that question. So an assignment will not be given for this week class, but the materials will be uploaded and the cohort leaders will let you know when to be uploaded. So an assignment not given for this week till next week, okay? We want you guys brain to be relaxed a bit. You don't want to rush, you want to take it as a pace, okay? So for this week, there will not be assignments till next week. Is that fine?
Yes, thank you very much, madam.
All right, you're welcome. So once again, thank you everybody. Asante sana. Thank you so much. Have a wonderful day. Bye everybody. Please join the WhatsApp group if you know you're not there. Please, we are begging now. Please join. All right, everybody. I remain your facilitator, Peace Roland, and bye till next week. Bye, guys.
Bye-bye.
Bye. Bye. See you next week.
Bye. Thank you.
See you next week. Bye-bye.
Thank you.
Bye-bye all.